in that video from the other day. How about multiple substituents? So we can have a couple of different scenarios. How about if one thing they can do is reinforce each other. Reinforce. So if we have benzene now that has, say, a methyl group and a nitro group on it, and we want to carry out a nitration reaction, so we're going to add a second nitro group. Now we need to decide, is the second nitro group going to go here, ortho to the methyl group, or here, ortho to the nitro group? And it doesn't matter what side it's on. And this is a nice case, actually, because the two groups reinforce their directing effects. So the methyl group is an ortho para director, so it's pushing energetically to have the nitro group here, ortho, and the nitro group is a meta director, so it's energetically pushing also to have the nitro group here, meta, and the methyl group cannot be para because the nitro group is already there. So in this case, there's only one product that could be formed. The two groups are reinforcing each other. So we'll end up with, this is what we started with, and we'll have the nitro group here. So that's all good. However, there are cases where they'll have an opposite directing effect. So now let's replace this, the hydroxyl group, and this is the methyl. I think these might be the same examples that were used there yesterday. So then here's about bromo. And this is really bad. Let's try drawing this again. It's a little better. Now, what we need to deal with is thinking about directing effects. This hydroxyl group is an ortho para director. This methyl group is also an ortho para director. So the problem is, when we add bromine, the bromo substituent, it's going to end up being ortho to one group and meta to the other. In other words, if the bromo ends up here in the upper position, it's good energetically, it's ortho to the hydroxyl group, but it's disfavored because now it's meta to the methyl group. And if we then do the same thing here now, it's the opposite. It's ortho to the methyl, meta to the hydroxyl. So this is really where that strong versus weak comes into play, is that even though they're the opposite in terms of their, or I'm sorry, they want to both be ortho or para, the stronger group is going to win energetically. So this is the one case really where we have to deal with the strong versus the weak. So here's our starting material. The hydroxyl group is a ortho para director due to resonance, primarily, whereas this methyl group is more induction. Resonance is usually energetically more important. So the bromo will end up ortho to the stronger group. Okay, and there's one more that was mentioned here yesterday, is with some considering steric effects. So let's have, I think I had a different example. This is we'll expand a little bit. Let's take an aromatic system that has a methyl group and a chloro group. Now here, these are both ortho para directors. Ortho para. And this is the exception. It's a deactivator, but an ortho para director. So let's think about where these, and what should we put on here? How about, just use bromine again. So now what we'd like to do is introduce a bromo substituent. And we have to choose, we have two ortho para directors. So if we look at the chloro, we could have the bromo here it would be ortho, or here it would be para. And then if we look at the methyl group, here it would be ortho, here it would be para. One more choice is if we put the substituent here to the right side, it's going to be ortho to both. So those are our different possibilities. Let's just draw them out. So let's put the bromo group here. I was trying to save enough space. I don't think I can. So we'll go down. Let's put the bromo group over here. Or let's put the bromo group there. So yes, you're right, Lorianne. So this bottom one is not going to be formed to any extent. So the left structure here, the bromo, it's ortho to the chloro, para to the methyl, so that's all good energetically. Same thing here in the right one. Now it's para to the chloro, ortho to the methyl, so that's also energetically favorable from directing effects. Now having the bromo here, ortho to each of these groups, that's fits in terms of the directing effects and what we would see. However, squeezing the big bromine in between these two larger groups is going to result in steric repulsion, so steric effects. So what you would end up seeing is that this would be a minor product. So generally, even though you could potentially form another product such as an ortho-para effects or due to directing effects, you're not going to have the larger group stuck in between the other groups. Okay, so that's just a bit of an intro into now thinking about adding more of these multiple substituents, and we can go on to adding 3 substituents and things like that. So now, in the interest of time, why don't let's bring up one more type of a reaction, and then we'll pause for a few minutes. I think that'll be a good place then to pause. Okay, so this will be a bit of a shift. Now, what we want to do is to couple different reactions with the addition reactions, with the electrophilic aromatic substitution. Electrophilic aromatic substitution reactions, if I can cheat, like this. And let's, what this means is one thing in particular. So we're going to review one thing and then bring in a new reaction. So remember, one, we have this Clemmensen reduction. We have a couple of reactions. This one we didn't really go through the mechanism, but imagine you have this acetophenone, so this ketone. We had a couple of ways of getting rid of a carbonyl group. We could take zinc and mercury, HCl, and heat, and we get rid of the carbonyl group. If we didn't want to use the mercury compound, we had the Wolff-Kishner reaction, Wolff-Kishner reduction, and we went through that mechanism just briefly. That was another way to remove a ketone, and that one used hydrazine, NH2NH2, and this one was a strong base, KOH, in heat, and that got rid of the ketone plus nitrogen. And then we had a third one, which was rainy nickel, about the thioacetal. So same group, and then step 1 was a thioacetal. Step 2 was RANEY, rainy nickel. So those were 3 ways to get rid of a carbonyl group. Now, a great question here is probably, well, why is this important for what we're doing now? And hopefully this will help justify this. So I'll make it a little smaller and scroll up so I can keep those there. Imagine you want to make, so the goal is to synthesize from benzene, it's supposed to be at an angle, starting with benzene, want to make this, I don't know, butyl benzene. Add 4 carbons. Okay, so that's the challenge. The problem is we cannot do this by the Friedel-Crafts alkylation. That would be the nice thing, is we take benzene and treat it with 1, 2, it's a nice straight line, but let's make it 1, 2, 3, 4 carbons. Aluminum trichloride. That would be nice. However, we're generating a carbocation-like species, so we always have to be on the lookout for a rearrangement. And so we're going to end up with this as our product. So that's not going to work. However, then we know that, so I'll scroll up, we'll come back to those. How about Friedel-Crafts acylation? It's supposed to say acylation. So now, what we could do, I'll go down here so I have a little more space, is take our benzene and treat it with an acyl chloride. So 4 carbons, again, AlCl3. And we know now this reaction, there's no rearrangement, because we form an acylium ion. So our product is going to be this. And now what we want to do, though, is our overall goal was to make, going back to the middle of the page here, this simple butyl substitution. So now let's just get rid of that carbonyl group. And I'll just use the first one, Clemmensen reduction. That removes the carbonyl group, or reduces it. So now this is actually an example of synthesis, is that if we're introducing some of these alkyl groups, a really powerful way to do this is to couple a Friedel-Crafts acylation, where you're not subject to rearrangements, and then reduce the ketone that's formed to form the alkyl group. So it's a 2-step process, but quite useful. And then just to follow on this, one more reaction. There's a new reaction that's also very useful here. And this one, it kind of comes out of nowhere, and we're going to leave it as a mystery in terms of the mechanism. But a very useful reaction is you can take an aromatic compound, and this position that's connected to the benzene ring is known as the benzylic position. And in OChem 1, you've seen a lot of useful chemistry there in terms of SN2, SN1/E1, elimination, radical reactions. But for our purposes right now, you can take at that benzylic position and use something like Na2Cr2O7, which is an oxidizing agent, sulfuric acid and water. And this actually generates a carboxylic acid at this position. So this is a very useful way to generate this benzoic acid. And why this is so useful is we know all sorts of reactions that you can conduct with a carboxylic acid. So you can react this now with SOCl2, thionyl chloride, and turn it into your favorite amide or whatever you might want to do. This reaction, as I mentioned, we're not covering the mechanism. It's likely complicated and probably involves a radical component to it. All we want to know in terms of our synthesis is that we can turn the benzylic position here into a carboxylic acid. What's unusual about this reaction is that it doesn't matter what the carbon chain length is. So it seems a little unusual because we haven't really explained any sort of a mechanistic basis for it. So what I mean is that you could have something, like this. You treat it with Na2Cr2O7, sulfuric acid and water. It could be one carbon, it could be 1,000 carbons. You still just end up with the carboxylic acid. It can be branched. And you could have branching here, all sorts of this sort of stuff. Still generates the carboxylic acid. So all that stuff gets cut off if you want to think about it that way. But you do need to have a hydrogen at the benzylic position. So if you were to take, just pull up just a little bit more, a tert-butyl substituted benzene, like this. Notice now, there's no hydrogen here on this carbon at the benzylic position. So the benzylic carbon. So if we were to take this reaction, Na2Cr2O7, sulfuric acid and water, no reaction. So you need a hydrogen. Doesn't matter if you have 1, 2, or 3. You could have an isopropyl group there, as long as you have a hydrogen. And then you'll form a carboxylic acid. And to Lorianne's question, if the other functional groups are attached to the chain, that's fine too. So you could have, be lazy here and not really draw it. So going back here to this chain, hexyl chain that we have here, you could have this decorated with a ketone, maybe a chloro or something like that, and then you'll cut it off here to generate the carboxylic acid. And you can also have other functional groups on the benzene. So if you have an ether over here, for example, you'll still get the carboxylic acid. Okay? So this is actually an oxidizing agent, a strong oxidizing agent as well. So it goes back to the Jones reaction that we saw earlier with chromic acid. This is sodium dichromate, Na2Cr2O7. And this can be used in a bunch of different reactions. One of the useful ones is the generation of a carboxylic acid here at the benzylic position. So to recap this recent discussion here in terms of a bit of synthesis now, is we can couple some reactions with the electrophilic aromatic substitution. So I wanted to review those ways that we saw to remove our carbonyl group, Clemenson, Wolff-Kishner, and Rainey-Nickel. This is important because a lot of times we might want to carry out a reaction here shown in the middle on an aromatic system, introducing an alkyl group. But a lot of times it'll be limited to rearrangements, or just because we cannot do the Friedel-Crafts reaction or alkylation on a deactivated ring. So you can couple that by using acylation, shown here in the middle now, acylation, followed by removal of the carbonyl group. So that's a good two-step process. Another good process is that you can introduce a carboxylic acid at the benzylic position. So you might want to do a bunch of chemistry on the benzene ring, and then at a particular step, treat it with sodium dichromate. That'll generate the carboxylic acid. So those are two very useful reactions coupled with our other 5 main reactions that we've seen. So why don't we pause here for 5 minutes, and I know